Perfect. All right. Thank you so much for the invitation and thanks for the great talk, Sebastian. I'm Alec. I'm a PhD student at Georgia Tech, and my project's going to be a little bit different than the past two. I'm going to be talking about kind of an interpretability work called ConceptAttention, where our goal is basically to visualize the concepts that are present inside of images generated by recently developed large-scale diffusion models. And so you've probably seen in the news recently, either whether it's text-to-image generation or video generation models. You might have seen this recent Studio Ghibli trend from OpenAI, from their AI image generation tool. These models are becoming effectively ubiquitous and have a lot of downstream applications in different industries. And at the highest level, underpinning most of these models is a technique called diffusion. And I'm kind of using diffusion as a catch-all to mean a variety of techniques. So that includes things like flow-based models as well, where the goal with these types of models is to remove noise from images and in particular for text to image, it's given a text description, can we remove noise from an image using a large-scale machine learning model? And do this kind of repeatedly until we can eventually generate an image that aligns with the given text prompt. So this is the technique underpinning most recent text-to-image generation tools. And this is kind of a similar story that you hear across a lot of machine learning and deep learning, where you have really big models, they have billions of parameters, their internal representations have thousands of dimensions, and you're processing thousands of image patches, pixels, tokens, etc. And then all of these kind of contribute to these models being like black boxes that are really difficult to interpret. You can't really tell what's going on inside, and it's difficult, at least initially, to kind of understand the internal mechanisms for how they work. And for a long time, saliency maps were have been kind of a go-to solution for explaining the decision-making processes of text-to-image models, or just vision models in general. The kind of classic example here is GradCam, where say you want to explain the decision-making process behind a image classifier. So in this case, say this classifier decides to predict dog. Why is it making that decision? Which parts of the image most contribute to that decision? And so this is something that GradCam can do. It can produce a heat map that tells you which image region is most important to making that decision. And people have tried to sort of generalize these types of approaches using various underlying methodologies to diffusion models, so to text-to-image models, where you can kind of create saliency maps that isolate the location of different textual concepts in generated images, but they either struggle with kind of poor quality, they don't properly localize objects very well, or they only work for a very primary object in the image, or they only work for a select few concepts, like ones that are in the prompt explicitly. And so this kind of limits these techniques' applicability in scenarios where you'd want to localize other objects that aren't explicitly referenced in the prompt but are still central to an image. And so this is exactly the problem that we aim to solve with our project, ConceptAttention, where we aim to create high-quality saliency maps from the activations of these large-scale diffusion models for any concept and without requiring any training. So at the bottom here, you can kind of see some examples of the saliency maps that can be generated by our approach if you're familiar with the Flux model, is what this is using. So yeah, the key advantages of our kind of approach that we aim to solve were producing better quality saliency maps than kind of existing baseline methods. One of the most common ones, if you're familiar with this literature, is to use the cross attentions of these models. So you can see that on the bottom here. We can significantly improve upon cross attention without using any sort of outside model, any extra training or anything. So this is kind of like a plug-in replacement for cross attention, which is really used in like dozens of works that require some kind of localization of concepts or objects in images. And like I said, our method requires no training, and it works for any concept, not just the ones present in the prompts. And you can even apply our method under the hood to cross-attention to allow you to visualize any concept as well. And it can be run in parallel. It's not a very expensive operation relative to the generation of these images already. You can run the operations in parallel. It doesn't have high latency, and there's minimal additional memory overhead for using our approach. And for practitioners in the audience, some of the practical applications of this, like beyond just kind of interpretability and understanding how these models work, are potentially you could use this to create segmentation maps by just kind of thresholding the outputs of our approach. You can generate an image, and then you can create segmentation maps of where objects in the image are. And this could be used to generate synthetic data to train, say, a semantic segmentation model, or for other kind of applications. And this is all using only a single pre-existing, pre-trained model, this large-scale diffusion model. And then another really practical application is image editing. So if you can isolate the location of an object inside of an image, like a car, okay, then you can only edit, you can restrict and edit to just that region and image. And so this is another application of our approach that's really practical. So even if you aren't kind of intrinsically motivated by understanding like how these models work on the inside from a scientific perspective, there are real world practical applications of techniques like this. So, and then a kind of funny story is I was talking with a friend of mine when I'd shown him some of the results I had on text to image models, and he was like, "Oh, well, have you tried this on a video model?" And I was like, "Oh, I don't understand much about how these video models work." And he was explaining this to me, and basically like a lot of the video architectures, video model architectures are very similar to these text-to-image models that I was building them on. So I was like, okay, I'll try and implement this one afternoon on a video generation model where really it just has this added temporal dimension, and it worked out of the box. So this is really like a benefit of the simplicity of the technique and the fact that it doesn't require any extensive or expensive training. It could kind of just generalize to an entire new model class and architecture. Which was really exciting. So I have a short demo, and you could even use this demo interface. I have a link near the end of the talk where basically like it's just showing you how you might use it. In this case for generating an image where you just, write a prompt, very familiar if you've ever used these text image models. Then you can just select some concepts that you want to localize in an image. And then you run the model under the hood. So it might take like, say 10, 15 seconds to generate. But like I said, not really, there's not really an extensive additional overhead compared to running the base model. And you can localize the various concepts that you specified. So in here, you can see like the presence of the dog, the trees in the background, grass, and then, an abstract concept like background, where it's like, what does that really even mean? It's not like a concrete, explicit object, but you can kind of see and gain some insight into how this model sees the image by uncovering the kind of like semantics of these representations. And then you see a comparison to cross-attention where qualitatively our approach seems to generate like a smoother localization of the dog, and then it works in general for various concepts, even though tree, grass, background, they aren't explicitly in the prompt. And then you can also use our approach on real world images. So you can upload a real image and write down some concepts that you want to localize, run it, and you can kind of use this model, these diffusion models, as an encoder. You're encoding the representation of a real image. So your goal isn't to generate an image, but it's to take advantage of the rich representations learned by these generative models to then say, oh, I can localize different concepts that are present in this image as well. And this is also really convenient for evaluating our approach and comparing it to other methods where we can really see, oh, like our method really does generate more localized saliency maps for real world concepts than other approaches. So now I want to talk a bit about like how does our method work under the hood, some more details about that. So some background, if you're not up to date on this literature, until kind of maybe about a year ago, 18 months ago, the state-of-the-art architecture underpinning most of these text image models were these UNet architectures, which have this kind of combination of convolutional layers and this kind of encoder-decoder architecture. And they also have a mixture of transformer layers, attention layers that are responsible for incorporating the textual information into this representation to guide and steer the model towards generating an image that matches a text description. And this is a standard approach that's been used in a bunch of models you might have heard of, like Stable Diffusion, the earlier versions. And like I mentioned, the way in which these models incorporate textual information is through cross attention layers. And the cross here corresponds to the fact that you have two sequences of representations corresponding to distinct modalities. So you have the text sequence where you input a text prompt and you kind of break it up into tokens, which are basically the words of this text prompt. And then you have patches, which are, just regions of the image, square regions of the image. And your goal is to say, how can I incorporate information from the text prompts into the image representation that I'm learning? And this is done through a very familiar attention operation, where you have queries from the image and keys from the text. And you compute the dot products between these representations. And then you eventually predict the next layer's instance of image representations. And people discovered that, oh, if I just look at these kind of associations, these dot products between the text features and the image features, I can kind of start to generate interesting saliency maps that show what the model thinks this concept is, or where in the image this model thinks the concept is. But you can kind of see they're not like necessarily the best. You can kind of see for the dragon, it does a pretty good job at localizing the presence of that concept, but it's not the best. So there's definitely room for improvement here. And keeping in mind, this is all really just an observation. There's no guarantees that this model is doing this. It's quite interesting that this is like an emergent phenomena that the underlying model just happens to learn as a byproduct of the task of generating images, which I think is pretty exciting. And in the past year or so, the state of the art for model architecture underpinning the biggest sort of most recent diffusion models is diffusion transformers. And this is kind of a familiar story in a lot of machine learning. Is like, okay, initially you had, say, convolutional architectures in computer vision, and now they're being replaced by vision transformers. And the same thing is really happening in the diffusion model literature, where the biggest, most recent models like Stable Diffusion 3, Flux, and then a lot of these video generation models leverage a variation of a transformer architecture to do image generation. And for text-to-image models in particular, they use a multimodal diffusion transformer, where the multimodal just corresponds to the fact that it's processing both the text and image modalities. And the architecture for this is actually, relative to even a UNet, quite simple, where you have a sequence of text tokens and a sequence of image patches. And then these are fed into self-attention layers that process a combination of both of these modalities. And you repeat a bunch of blocks like this and generate an image. So there's no bottleneck architecture. You really just have a bunch of repeated similar self-attention blocks. And it's similar kind of to cross-attention, but there's some key distinct differences. You use an attention layer to process both modalities, where for both modalities you have the familiar keys, values, and queries. And then you compute a self-attention on the combined sequence of these modalities. And that produces a set of output vectors for both modalities. So that's a bit different from cross-attention, which only produces an output sequence for the image. And you might ask, oh, does cross-attention still work here? You do have cross-attentions as kind of a subpart of this operation, where you can still look at, okay, I have the text keys and the image queries. What are the associations between the two? What do they look like? and you can display them, and that does generate cross-attention maps, and they're pretty high quality, and a lot of that could be maybe attributed to the fact that the model is just much more powerful and bigger than previous unit-based architectures. But then I kind of, one of the problem framings of this project was, oh, okay, like, are there unique properties of these diffusion transformers that can enhance their interpretability? Is there some other aspect of these models that we can use to understand how they work, and to display and interpret them? And that's actually true. So instead of looking at the cross-attention similar to the unit literature, we're like, oh, well, you have output vectors for both modalities, for both text and image. And that's something that's just that doesn't exist for these unit models with cross-attention. So we're like, oh, what happens if you project the image output vectors onto the text outputs? Does this space have some kind of shared structure, some kind of semantics that we can investigate and look at? And can we use the text as a way of as a lens into these rich image representations? And this is exactly what we did. We take the dot product in this output space, and this produces much higher quality saliency maps than cross-attention, something that's not possible with previous architectures. And I mentioned how one of the problems we wanted to solve was like, can we do this for any concept, not just concepts in the prompt? Because when you're generating images, a lot of concepts are implicit, like the background of an image. You're not going to say, oh, an image with a background. That doesn't really make a lot of sense. And then also as a tool for investigating and interpreting a model, you don't want to have to change the prompt in order to visualize concepts. That kind of hurts its ability or its efficacy as a tool for interpretability. So what we really want to be able to do is visualize any concept. And so we extended our approach to open vocabulary by adding a set of these augmented concept tokens, which are treated as basically text tokens because they correspond to text concepts. But what we do is we only allow the information in these attention layers from the prompt and from the image to influence the concept tokens, but we don't allow the concept tokens to influence the image at all. And so in this way, we create a set of contextualized embeddings by taking advantage of the existing parameters of the model. And these concept embeddings, these concept tokens can be used to interpret the image representation, but it doesn't influence the image at all, or the appearance of the image. And as I mentioned before, this doesn't really have a hugely prohibitive cost. It doesn't add a ton of latency, and it doesn't add a ton of memory overhead. And the latency is because this can be run in parallel. We can cleverly use attention masks in a single attention operation to make it so that the text concepts or the concept vectors don't influence the appearance of the image, but they're contextualized to those representations because the information from the image and the text prompt influence the concepts. And this can be done all in parallel. And also because we have, in general use cases, so many more image patches. In the Flux model, for instance, you have a 64 by 64 grid, which is around 4,000 image patches. In realistic settings, you might want to interpret 10 text concepts. You're not really going to be doing thousands. So the additional memory and computational overhead of this is really relatively minimal. So it's not prohibitively expensive to run. And like I said, it reuses only the existing parameters of the model, doesn't require any additional training. So you can readily apply this to a new model as soon as that model is released. There's not like an expensive training approach. And like I showed before, this approach produces higher quality saliency maps than a bunch of existing approaches, specifically like cross-attention across different models. And we evaluated it, this is the obligatory big table, you have to add. We evaluated this extensively compared to a lot of baselines on multiple architectures on zero-shot image segmentation. Because like I said, you can take a real image and encode it into the model and create segmentation maps by thresholding our coefficients that we produce. And it does a lot better than a lot of existing approaches on commonly used benchmarks for investigating zero-shot interpretability methods. Yeah, and that's all I have here. So yeah, this is our project, and this is a group effort. So thanks to my co-authors as well, and thanks for the invitation.